Hello everyone, welcome to our second video lecture on R. As a reminder, these video lectures are optional and they are designed to build up the skills that you're going to need to present the extra credit assignment at the end of week 5. So in this second video, we are going to cover an introduction to plotting in R. Let us get right to it. So when we talk about plotting in R, we talked about the creation of visual representations for data using the R already built-in graphical capabilities. So this is just referring to a bunch of functions that are already made available to you so that you can plot your data, so that you can create visual representations of your data. And as we saw on 10A, this is often regarded as a very useful step when doing research because it gives us an idea of what our data looks like. Much more easy to open the database that we collected when running an experiment and trying to make sense of all the numbers that are there. It's way more easy to interpret what's going on if we just take a look at a plot. So plots are useful precisely for quickly visualizing and summarizing data, and that can be used to explore and understand patterns in the data. So the first type of plot that we're going to cover in this class are called scatter plots. A scatter plot is a specific type of plot that displays data points on a coordinate plane. Scatter plots are useful for visualizing the relationship between two variables that we have observed. Here is a little worked in example of how to build a scatter plot in R. Let me build it up with you. Again, we go to our RStudio Cloud. I have already signed in. Last week we created this toy project, so it again takes a little while to open. All right, and then our working space is open again. As you can see here, there is already a file open that corresponds to the code that we worked last week. It looks a little different from what we saw on the last video, just because I have added all these comments. So comments are, as the name suggests, little notes that I write for myself or for other users to understand better what I am doing. And they have the peculiarity that they all start with this little hashtag symbol. So in R, whatever you write after a hashtag, it's going to be read as a comment. What does that mean? That means that when I run my code, all these comments are going to be ignored. So I'm going to now open a new R script. I'm going to save it now, give it an informative title, R code week 2. Whoop. Again, I am working with a different keyboard. So R code week 2 is going to contain the results of working today with our plotting functions. If we go back to our PDF, I'm going to copy this data here, these two variables here that are going to serve as toy data for this lecture. And then I go back to my RStudio Cloud, I copy them. The environment is empty. Again, I select them. I hit Control Enter. I have run exactly these pieces of code. And now I have run my instructions here, and I have therefore created two variables with a value, with a numerical value each that covers the numbers between 1 and 5 and 2 and 11 in increments of 2. Both of them cover a total of 5 elements. So a scatter plot is really easy to develop in R. We are going to be using our plot function, so you can sort of see here how it is described as the kind of the default plot that we can create here. And my plot function, as we discussed in our last video, takes as input a vector of values to place on my x-axis to draw on my x-axis, and a vector of values to draw on my y-axis. So if we do this and we run this little code, oh, it says that the figure margins are too large. That just means that I have to make the space bigger. Again, I select it, run it, and I have run my little scatter plot. Now, so there are two things that I want you to notice here about the scatter plot. First is that what makes a scatter plot is that it just shows the correspondence between my two variables as positions in our coordinate space. Scatter plots are used to show the relationship between a numeric variable on my x-axis and another numeric variable on the y-axis. And typically, the way that we arrange these two variables to be located on the x and y-axis is that I am going to use the y-axis here to denote whatever is my dependent variable. So we are going to plot here whatever variable we think is changing as a function of the different values that I have on my x-axis. So the x-axis plays the role of the independent variable, the variable that we are either manipulating or the variable for which we are observing its effects on y. This is also of y, for example, when we talk about linear regression, we give this x variable here the name of predictor, and y becomes the response variable. The y changes as a response of our changes in x. The other thing that I would like to emphasize here is that whenever we have a scatter plot, the observations that we have here on X are usually independent from each other. So this is the equivalent of going out to the world and saying, I am going to observe variable X, say for example that X is, I don't know, the age of a baby. So I have my different values here. And then I record a second variable Y that can be, I'm making this up, the number of hours they spent in front of the TV. So now what I am seeing here is that I observe that for the one case where the baby had a year old, the mean number of hours they spent a week watching TV was just 2. Then for the baby that is 2 years old, I observe someone that somewhere closer to 3 hours of TV screen time on average here, and so forth. So the idea here is that these babies are different babies. They all provide different values for their age, but still they can all be associated with a different value of the response variable. Here, the point that I'm trying to make is that all these values are values obtained across instances that are kind of like independent from each other. This is what the scatter plot looks like. So again, a graph that shows the correspondence between a numeric variable and another numeric variable, with X playing the role of the independent variable that we assume might have an effect on Y, and each instance of X corresponding to an independent observation. Then we are going to go to our next type of plot, which is a line plot. Now, a line plot is a type of plot that displays data along a number line. Line plots are useful for showing trends of a variable over time or another continuous variable. Here is an example of how to create a line plot in R. So I think this is the same data. We're also going to be using our plot function. The only difference now is that now I'm going to add this little argument to my plot. So if we go back to our RStudio Cloud, I'm going to just copy it in a different line to keep them separate. Now, if I use the exact same function, but I add here a type L, that L stands for line plot, and I execute this. Now what we're going to see is that now our very same plot goes from being a scatter plot to being a line plot. And what is the key difference here? I mean, the information that is presented is mostly the same. We are still seeing the relationship between a numeric value on the x-axis and a numeric value on the y-axis, but the difference relates here on the implication of this line. What this line is suggesting is that we assume now that all these values, in between them, there might also hold a relationship between the value that we get on y and the specific value that we have on X. So if we go back to the example where we thought that X was the age of babies. Now, in this particular example, if we are presented with a line graph, we might immediately jump to the conclusion that all this data come from the same baby over time. So now they are no longer independent observations or separate observations of just a given value for this variable. We are now observing how this variable changes over time and how those changes have an impact on my dependent variable here. So by building a line plot, I'm saying, well, when my son was 1 year old, he watched an average of 2 hours of TV every week. When he turned 2, he was watching roughly 3 hours a week of TV. And what that is saying is that because of this increment, we are sort of also implying that when my baby was 1.5 years old, then he must have watched whatever number is here, like 2.7, 2.5, something like that. So again, what the line represents now is that now we are not just simply checking the correspondence between a set of individual observations of my predictor variable and the dependent variable, but rather that we are now assessing how our dependent variable changes as a function of how this variable changes over time. So that is the key difference here with the line plot. In the scatter plot, we assume that all these babies are different babies. So these are simply different kids that I have observed, perhaps in my family, different nephews or whatever. But here, where we are using a line to connect them all, we are more keen to interpret that as evidence of being a single child for which we are observing this variable across many points in time. Now, let us keep digging a little bit deeper into the difference between scatter plots and line plots. So let us say that instead of having this beautifully ordered data that we have here for my x-axis, we have something like this. So a new x variable, I'm going to overwrite it, that contains all the sequence of numbers. And as you can see here, the sequence of number is not ordered. And more importantly, there are some repetitions here. So right now I cannot really use this because if I try to plot this against the y variable that I already have loaded, this is going to tell me that they have different lengths, right? So that is a key component of both my scatter plot and my line plot. They show the correspondence between a value that I have observed of x and a variable that I have observed of y. So there need to be the same number of them. They come in pairs. So let me just write a new y variable. So again, let me build up this new variable y that is going to contain this sequence of numbers. The sequence has the same length as x so that we can build our scatter plot. And it contains a bunch of random numbers that I just typed in with my keyboard. If I run this, then I have now, executed my instruction here. I made the console a little smaller. And then we can see that we have overwritten our previous y value here. Now it has 19 different values and it contains all the numbers that I have typed here. If I now build a scatter plot, we get here a nice little scatter plot that just shows the correspondence between each individual value that I have here on x and the corresponding value that I observed on y. So now say, for example, that this corresponds to the number of correct answers someone got on an exam 1, so the first exam of the quarter. And then let's say that y is now going to be the number of correct answers someone got on the second exam of the quarter. So let's call them the midterm and the final. So now what we can see here is the correspondence between this grade here as a function of this grade here. So we are seeing that there seems to be like an overall trend. It does seem to be the case that the better I did on the midterm, the better I did on the final. That actually turned out to be totally accidental. I did not plan that, but okay. And more importantly here, because we have separate dots, we get the overall intuition, hopefully, that this all corresponds to grades obtained by different people, right? So hopefully we have now developed the intuition that each of these dots corresponds to a different student, right? Because there are multiple cases that fall on the same value. So for example, here we have 2 cases in which the score in the midterm was 1. Well, in reality, there's 3. So there should be this one, and this one. But trust me, you can stop the video and count for yourself. But what's going on here is that here we really have 2 points overlapping each other. You can see that if you count the number of spaces in which the 1 falls, we have 2 cases where there's 1 on x that corresponds to a 5 on y. But anyway, the important point here is that because we have 2 instances with the same value, this could not pertain to the same object or the same element, the same subject being studied over time. This is clearly just a collection of values that I have independently sampled. This is just a set of independent, non-related, separate observations that I have collected across both variables. The only thing that should be the same, of course, is across variables. This person here that got this score on x is the same person that got this on y, and so forth, so forth. So the only correspondent really is across variables. But between each individual observation, each pair of observations comes from a totally different entity. And now the point that I wanted to make here is that now if I turn this into a line plot, we get this funky, horrible looking thing. And that is again because the way that line plots work is they connect each individual pair that I have drawn using my scatter plot. And that does not work here for several reasons. The first one has to do with the fact that when I inserted my 2 variables here, they are not in order. So I could try to solve this using my sort function that we saw last week. So if I sort both the x and the y variable here using my sort function and I run it again, I should get something that looks a little cleaner now. But we still know that this is really not correct. Again, how do we know this? Well, because the line plot is supposed to show us the relationship between a variable in y that changes as a function of how the variable in x change over time. So we are forcing our graph to look like a line plot, but we know it isn't. Why? Because by sorting both the y and the x variables that I had here, I have broken down their relationship. So it is not longer going to be the case that I am correctly representing that when I recorded this value for x, I got this value for y. So that is broken now because I have just rearranged both of them. And secondly, even if they were not presented this way, so even if I had here just y, and I still get something that looks like a line that shows some form of tendency here, we can certainly see that this line plot is not correct. For example, here, if we go to an x value of 2, we see a vertical line here that is hinting to the fact that we have more than one number 2 in our data, and we do know that that is the case. Similar thing happens here on the value of 1, on the value of 4, on the value of 8, and so forth. And that is a problem because then I'm not going to be able to describe what is the value of y that I observed when x was 2. I got all these possible values of y. That doesn't really make any sense. As we know from math, whenever you have a function that assigns multiple values to a same value of x, we call that an invalid function that is unsolvable. We cannot solve that function. And again, it kind of looked nice if we did this, but again, we know that we are forcing the graph to look like a line plot, but it does not have any sort of meaningful interpretation for me. So let us be very careful with that. And with that, I think we're ready to move to our next type of plot. So next we have histograms, which you should already be familiar from what we have discussed in 10A, hopefully. So a histogram is a type of plot that displays the distribution of a numeric variable. Histograms are useful for visualizing the shape of the distribution and identifying patterns in the data. Here's an example on how to create a histogram. We're going to generate some fake data, and then building histograms is as easy as using the special hist function. This code generates a histogram for the data X, and the bins that are generated are automatically determined based on the characteristics of my X vector. So again, I can go to my RStudio Cloud, and let's agree that this is wrong. Again, I was just trying to clarify how not to use a line plot. The correct thing here would be to simply use a scatter plot. Okay, and let us move to a histogram. Again, let us work with one of these two variables. Let's say X. I'm going to do hist, the special function to build histograms. And what that is going to show me is the distribution for the number of times, that is what frequency here means, that each individual value containing my vector X appears. So notice here that what histogram is doing is I am feeding it a bunch of numbers and it's counting them for me. It's saying, okay, how many times in your X variable does the number 2 appears? How many times does the number 6 appears? And so forth. So sometimes the histograms are a bit hard to read when we have small collections of data. What do I mean by that? Well, we mean here that it's difficult for me, for example, to immediately, from just looking at the histogram, ignoring the fact that I have access to my data, it would be a little difficult for me to know exactly how many numbers do I have. Is it this bin here or is it this bin here? So let us try to work together how to process that by reviewing other useful functions in R. So we're going to now work with our table function that you should also be familiar from 10A. Table is a useful function. It sort of does the same as the histogram, but instead of showing you a nice little picture, it's going to take in a vector of values and it's going to count how many times does each individual value appears on my script. So it tells me that the number 1 appears 3 times on my vector, the number 2 appears 2 times, and so forth for each individual value. So using our table function, we can sort of get an idea of how our data points are being grouped together. So from here, it seems to be the case that 1 and 2, the counts for 1 and 2 are being put together. That is why we have a count of 5. The next bin, for example, here would correspond to the number of number 3s that I have. The next bin would be the number of number 4s that I have. The next bin would be the number of number 5s that I have, and so forth. We have then 4 bins here with a height of 2. That is exactly what our count says. So again, a raw histogram might not be as precise as we might want it to be, but it gives us a general idea of what data looks like. So we know, for example, that we have 5 values that fall below 2, and we also know that the remaining values, for example, here, the numbers from 5 to 9, seem to be equally present or equally represented in our vector. Let us now move, for example, to the y vector that we had there. And now we see that in here, kind of like the opposite happens. So the first values, all values below 8 seem to be represented roughly the same amount of times. But we only have a couple of instances where we have values larger than 8. And we can sort of see here, visually here, we only have 1, 9 and 1, 11. Those are the numbers that are being represented here. So the last type of plot that I wanted to cover for this video is called the bar plot. And the bar plot, it's going to be very reminiscent of the histogram, but it represents something entirely different. And that is why I wanted to mention it here. So a bar plot shows the relationship between a numerical variable and a categorical variable. That is the key distinction. We have not had anything like this before. Bar plots are useful to make comparisons across groups of elements. Here we have an example of how to create a bar plot. Again, we have some fake data. And here is a little line that creates the bar plot. Oops, I didn't change this label. This should say bar plot. It's going to be correct when I upload it to Canvas, but right now it's wrong. So this one is correct. This is the function to generate bar plots. So this code generates a bar plot that treats each value in X as a bar height. And the number of bars in my bar plot is going to be determined by the number of elements that I have in my vector. So what does that mean? That means that when I go to my R console or my R workspace, And now if I do bar plot, this is also a built-in function, and I feed in the vector of values x, what this is going to do, instead of counting the number of times that each number appears, it's simply going to interpret each of these numbers as an indicator that I'm giving to it for the height of each individual bar in my plot. So what this is saying, imagine that x is now again the number of correct responses someone got on their midterm. Now what I'm doing by putting this into the bar plot function is I'm saying, plot each of these values as the specific count that I got for a specific participant, for a specific student in the class. And that is what we have here. This is now showing the correspondence not between a numeric variable and another numeric variable. Now what we have here on the x-axis is now a categorical value, because now I know that each observation, what it really is representing is a different student. So now what I'm saying here is that this particular bar here indicates the count for the number of correct answers that this person got. Now this in the x-axis is a label that corresponds to a person. This second bar here is showing me the number of correct responses that this second person got. Again, there is not a number here. This is the name of the person. Even though I'm saying the second student, and that is probably hinting you to the fact that you could use a number, that is really not true, because there's nothing that inherently makes this person the second person. This bar could have been placed at the very end of the bar plot, and it would mean exactly the same. And more importantly, opposite to the histogram, where we do have a correspondence between a numeric variable, being the frequency, the number of times something happens, and the specific value that I observe here. This is something that does carry a numeric meaning. We are saying here, what is the number of times that a value falling within this range appear on my data? So again, this is showing me the correspondence between this value here and the number of times it appeared. Now on the bar plot, I am simply showing the correspondence between a numeric variable, so what is the value that I have captured, and a categorical value signaling the observation that I just made, which in this case corresponds to a different student. Okay, so now we're going to talk about customizing plots in R. This is what makes working in R for making plots the most interesting or the most useful. So R provides many options for customizing plots that allows us to change the appearance of the plot. It allows us to add labels and titles that are specific to our research or specific to our interest, and adding additional elements such as points, lines, colors, text, whatever you want. Here is an example of how to customize a scatter plot in R. This is the data that we used at the beginning. We are not going to use for new, longer data. And now we're going to be expanding our code. So now notice here, despite that this looks like a wall of text, everything that we have after this hashtag is just a comment for us to know what we are doing. And the only thing we're doing is we're adding more arguments. So we're still going to work with our plot functions that takes as main inputs a vector of elements to plot on the x-axis and a vector of elements to plot on the y-axis. But now we're going to add all of these different arguments. Let us see what they do. Let me copy this and paste it onto R. So before we run this, let me take a look at what our scatter plot looked without all these fun little arguments here. So let's go back to our scatter plot here. This is the scatter plot that we had in hand before. So now if I run all of this piece of code, I'm going to get something much more beautiful. So what I have done now is I have added all these arguments, and by doing that, I have personalized my graph. So the first argument that we can see here is the main argument. The main, as the name suggests, gives a main title to my plot. Then we have the xlab argument that simply assigns a label to the x-axis. So again, we have added this label here, x values. Then we have the y label that assigns a label to the y-axis. So again, this is going to be my new title here, and we can see them already reflected here. Then PCH, I don't exactly know what PCH stands for, but I know what it does. And what it does, it changes the shape or the particular presentation of the points that I am using in my scatter plot. So by default, I think the value is a 1, which is our classical non-filled circles that we used to have before, but we can play around with any given number. 16 is the one that corresponds to the enclosed dots here, but you can play with any other number. So just choose a number at random and see what we get. So this, for example, results in these funny little squares with cross inside. 15 is another popular one, so you can choose whatever. And then col is the argument that controls the color of the dots that I am presenting on my space. As you can see here, color is indicated with a label that corresponds to the color. R already has identified many colors, so pretty much all the basic standard colors that you might think of are already going to be distinguished here. So we could do green, we could do blue, we could do yellow, we could do orange, all of those. If you want a particular funny looking color, I encourage you to go to Google, search R color. Then you're gonna look this nice little PDF here that contains the code for multiple colors in R. And then it is that, for example, you're like, oh, I like this one. So you go here, you take a look at the name, you just copy it. Then you go back to your art, then you paste it here. And now it is automatically going to redo my plot in that nice little color. So again, let me go back to the slide. This code, we have already verified that generates a scatter plot that has a title, labels for the x-axis and y-axis. It filled the red circles for the data points, and it preserves the default settings for all the remaining arguments that we have not covered here. So this here is just an example of a few of the many arguments that you can personalize when working with R to do plots. And we said before that the way to know which other arguments we have is to do comma, and then we do tab. And this is going to tell us, for example, right now, what other options of things to personalize we have here that we have not used yet. So let me cover a little bit of those briefly. I'm going to remove this parenthesis, leave the comment there, move my parenthesis at the end. So let us cover a new argument. So type again is the one that we used when we wanted to convert our scatter plot into a line plot. So let us use that right now. Also, we know that's going to look very, very messy. But again, it adds a line. There are other types that we could use. Type P just means draw points. We could also do B, which here again is going to look messy, but this is to illustrate what B makes. B is kind of like in between doing a line plot and doing a scatter plot. I suggest you use B whenever you can use a line plot, but you are unable to see what the specific points of conversion between the X and the Y values are. So for example, if we go back to the first data set that we had here. And if you remember when we did our little line plot, well, it might be the case that here it's a little difficult to spot where the number 3 coincides with the Y variable. So if we do instead of L, we do B, this is going to still show us the line plot, but now it's going to tell us exactly the points of correspondence that I have observed in my data. So this is going to be a little easier to read. Let me go back to our previous data. Let me show you what our plot used to look like, and let's continue working here. So again, we said that type B is not really going to be for us. So let's go back to type P. Let's continue exploring other arguments. So we had xlim, which as the name suggests, helps me to specify the limit of the x-axis that I am presenting here. In other words, I am going to show the range of values that I want to include here. So this graph starts at 1 because that is the least value that I have on x, and it ends in 9, I think, because that is the largest value that I have on x. Let's say that I want this to be a square space. So I know that the minimum value that I have on X is 1, the minimum value that I have on Y is 0, so I'm going to use that one instead, and the maximum value that I have in X is 9, but the maximum value that I have in Y is 11, so I'm going to use that instead. So now what I'm going to be doing is I am going to be setting up this space so that it covers all values between 0 and 9. And similarly on the Y-axis, I'm going to cover all, oh sorry, I said 11. I'm going to do it this way, and now our space is going to look a little bit more like a square. Whoops, it shows an error because I made a little mistake. I had 2 X limits. So it had to be Y-lim. And now what I have seen is I have retrieved my nice little plot. Again, the lines are gone because we have gone back to the P type of variable. And as you can see here, we have sort of like zoomed out. So now we are covering all values between 0 and 11 here, and also 0 and 11 here. So we are kind of like zooming out in our plot. Another value, another argument that you can change. Log is not something that we're going to care about. This just serves for doing logarithmic transformations. Sub is going to help us put a subtitle to the plot. So let us here write the name of our class, and I run this all again, and we are using here a little subtitle. I don't really like that, so I'm going to delete it. So the next argument that I can modify here is n. And takes as input a logical value, true or false. And what this is going to do, so the default is true. What this is going to do is this is going to control whether the labels or the titles that I have here, so this main title here, the subtitle here, the X label here, and the X label here and the Y label here appear. So if I do and equals false, this is all going to disappear. And what is the purpose of that? Outside of the plot function, there are other functions in R that you can use. So for example, we can use the mtext function. M stands for margin. So this mtext function, for example, allows you to input some form of text on a specific side of the graph. So we would start counting here. So this is the side 1, 2, 3, and 4. And more importantly, why would you want to do that outside of the plot function? Because it contains other arguments that allow you to have a better control on how the marginal text appears. So let's go back to a plot where we had them. So for example, here, it might be the case that I think that this space here is a little bit too big. This space is a little bit too big. This space here is a little bit too big for my taste. So I could always just do those labels by myself using the mtext function, my scatter plot. And then for side, I'm going to do 1, 2, 3. So I'm going to do the third side. I want it to be, let's say, right on top of my plot. I'm going to do line 0. Line represents the distance between the edge or the margin of my plot and the place in which my title is or my text is going to be plotted. So let's see so far, how does this look? Yes, so we have here my same title right outside of the margin. It could be that I want to distance it a little bit more. So let's say line 1, I run this, it goes further away. Let's say that I want 0.5. So that looks a little bit better for me. Then I can edit the font. That's what F stands for. F2 is bold font. F3 would be italics. I don't know if F4 exists. Oh, F4 is that italics and bold. That looks nice. So let's keep it that way. Anyways, the idea here is that I have canceled here my default main argument just so that I can get greater control and specify it myself and make my plot look very beautiful. Similarly, this is the last argument we're going to cover because we have done a lot. We have the axis argument. The axis argument works very similar to the and argument, except that it doesn't work for titles. It works for the axis, as the name suggests. So axis takes a logical value. It could be true or false, and it's going to control whether I'm going to be using this default axis that come with my built-in plot function. So I could do axis false and run this whole thing, and I have just disappeared my axis. And again, oh, why would that be? Well, because now I have the option of using an outside function axis that helps me build my axis and specify, as you can see here, by the multiple arguments that we have here, it helps me personalize a lot. So it helps me specify in which side do I want the axis to be, what are the positions that I want to cover in my axis, what are the labels that I want to give to it. So for example, this is going to be very useful when we're talking about the bar plot. So instead of having numbers or placeholders, we could have specific names for the variables that I have on my x-axis or y-axis, for example. Here we denote whether we want it to have a little tick. So this tick represents this little line here, whether I want to include that or not. Again, the distance from the margin. So whether we want it to be right outside of the plot or we want it to be a little bit more distant or even more inside the plot and so forth. So let us just say, for example, that I want to place an axis because currently my plot does not have an axis. Let us say that I want to place an axis at the second side. So this is going to be on my y-axis here. So 1, 2, 3, 4. And say that I want to place it at all values between 0 and 11, right? Because those are the boundaries of my plot. And for the labels that I want to place at each of those locations, well, let's keep just the same numbers. So again, if I run this whole thing, I would get again back my y-axis, but now we can see that unlike what we had before, where we had kind of like only a tick every 2 values, now I have a tick for every single value that I have observed because that is the way that I have designed it to be. I could also put it closer or further away from my plot. I could put it inside my plot for whatever reason that could be. And that is why there could be an interest for doing axis false, but then personalizing the axis outside of it. So there is that. All right, so that is all for today. In a couple of hours from now, I'm going to make available both the code that we worked together last week, which again has already incorporated some comments so that we can all follow along what we were doing and remind ourselves what we were doing and why we were doing that. I will make available the code for this week as well. We still have potentially a lot of things to talk about, how to personalize the histogram function and the bar plot function, but I don't want to overwhelm you. I know that this has been too much. So the plan for the next 2 weeks is that, so next week, we're going to talk about the opt-in function that is going to be very useful for the remaining lectures in the class. We're going to talk about that in regards to built-in functions and user-built functions. And then on week 4, before you submit your assignment, we are sort of going to rewind. So try to cover again all the materials that we have covered so far. except that now we are going to do it in depth. So we are going to now cover the details of things that I did not have the time to talk about in terms of how to define variables, how to manipulate variables, how to build nicer plots. So we're going to work with the arguments we can use to personalize the bar plot, histogram plots, and so forth. And perhaps cover a worked example together so that you are all ready to do your extra credit homework. With that being said, I hope you have a magnificent weekend. See you next week.